Okay, we're looking at the velocity of each time interval. Okay, so reminder, we're gonna call it velocity is equal to a change in position over a change in time, and we're gonna just call this one v1. Okay, and that's gonna equal x final minus x initial, time final minus time initial. Okay, so for this section here, my x final was at a positive 10 meters, and I'm minusing that from the initial, which was, so we're minusing from a negative 5 meters. Okay, and our time interval, our final was, let's see, at 10 seconds, and then our initial was 0. Okay, so we have 15 meters divided by 10 seconds, so velocity 1 is equal to 15 divided by 10, and so now we have a 1.5 meters per second. Okay, so now let's look at V2. Now we talked about this. Our change in velocity here, or sorry, our change in position here, our final position is at 10 and our initial position is at 10. So 10 minus 10 is 0, and anything over 0 is still 0. So, and the slope of my line here is 0. So velocity for this second is 0 meters per second. Okay. And now for our third, V3. Okay, so x final here is a positive 15 meters, and then my initial was 10 meters. That was my position initially. Now the time component here. When my final time is at 30 seconds, and my initial time for this interval is at 20 seconds. So we have 5 meters over a span of 10 seconds. So my third velocity is 0.5 or 1/2 meter per second. Alright, now let's continue. You're standing at a position of 0 and roll a marble which moves with the motion described by the graph. Explain the motion of the marble as it moves along each segment. Okay, so we're going to describe this motion. So when I look at this, I'd say, in a time span of 3 seconds, my marble moved from position 0 to a position of positive 30. Okay? I'd say that this happened at a constant velocity because the slope of this line stayed the same. Then the marble sat at a position of 30, and it sat there for 3 seconds, right? We went from 3 to 4, 4 to 5, 5 to 6. So that occurred in 3 seconds, just sat at that position. Then it went from that position of 30 down to a negative position. That looks like it's right at that negative 20. So we went from a positive 30 position to a negative 20 position, and that occurred in another 3-second time frame. We have a negative velocity because our slope is negative, but constant. So it moved at a constant negative velocity from a position of positive 30 to negative 20 in a matter of 3 seconds. Okay. Please rewind, listen to that again, pause, and so you can kind of describe all that motion there. Okay, we're going to calculate the velocity along each segment of the path of the object whose motion is described by the graph. So it's very similar to what we did last time. We're going to call this section 1, 2, 3, and 4. Okay, so velocity 1, x final, position final, was at 6 meters. Position initial was at 0. And time final was at 3 seconds. time initial was 0 seconds. So we're going to have 6 meters divided by 3 seconds, or 2 meters per second. Okay, so that was our V1. Now, V2, our slope is 0. We didn't travel any distance, we didn't have any displacement in an amount of time, and so that's 0 meters occurred every second. Okay. Now, for V3, our position final was 3 meters. Our position initial was 6 meters. Our time final was 8 seconds, and our time initial was 5 seconds. So we have -3 meters occurred in 3 seconds. So we have -1 meter per second. Moved in the negative x direction, 1 meter every second. And then back to our velocity of section 4, exactly the same as section 2. We stayed in the same position over some span of time. In this case, it was 2 seconds. And so we had moved 0 meters per second. Okay. We can get your work here, or I guess I probably should have brought it down there. All right. So now that we saw it with the position versus time graph, we're going to look at a motion diagram. I need to check on my time there. Okay, so we're going to look at this motion diagram. And these arrows no longer represent displacement, they represent velocity. So remember, vectors, the length of the arrow represents the magnitude, and then the direction of the arrow represents the direction that it's occurring. So notice we had the exact same velocity. We'll call it, oh, I don't know, 15 miles per hour, because it looks like we're talking about cars here. So we're traveling 15 miles per hour, 15 miles per hour, and then the driver hit the gas pedal. So this one might be a hair longer, or you say it's still 15, but now we're really increasing in velocity. This is, what, almost double. So we could say it's 25 miles per hour now. And then the driver sees a police officer, so they push the brakes. And so they're still traveling in the positive direction. So we still have a positive velocity, but it is less than it was before. Okay, so this looks like it might be slower than what we had here. So we're probably at like 10 miles per hour, and then at like 5 miles per hour, and then we come to a stop because there's no more velocity vectors. Okay. And now let's look at this idea here. Okay, so we know that this is our average velocity, and that the slope of the line here is velocity for a position versus time graph. Okay, in this situation, y is the position, and x is time. Okay, so the slope of the line for this object here is -5 meters per second. At time 0, we see that the object is at plus 20 meters. Now, B means y-intercept. So see how this graph, this line, intercepts our y-axis at 20 meters. Okay, so that's what's saying here. B is actually equal to our initial position, which was 20 meters. So our position is the same as the value of y in the line equation. So like we said, the y here is position. Okay, and so that would be our y final. So then we can describe this as an equation. We can say our position, our final position, is equal to the slope, which we know is velocity, times by x, which we know is time, plus my y-intercept, which is my initial position. Okay, so we have this great equation now that we're working with. So we have two cars. We have car A and B, and they leave school when the stopwatch reads 0. So car A travels at a constant 75 kilometers an hour, and car B travels at a constant 85 kilometers an hour. So first question, how far are the two cars from school when the stopwatch reads 2 hours? Okay, we know the velocity, we know the time, and we know the initial position. It's asking us to solve for x final. Check my time. Here we go. So when I look at this, I'm going to say I want to know how far the two cars are away from the school, so that would be my x final. So x final is equal to velocity. Let's do it. Let's see. This is going to be for car A. Okay, so car A travels at a velocity of 75 kilometers an hour. And then it went over a time frame of 2 hours, so that's going to be multiplied by 2 hours. Okay. Plus the initial position. How far are the two cars from the school? Well, let's make the school here our 0 point. So my initial position is actually 0 meters, and then we're traveling to some x final. And there's our x initial at 0. Okay. So when I plug this in my calculator, I'm going to take the 75 miles per hour, I'm going to times it by the 2 hours, and I get 150 meters. Okay. Sig figs, we took 2 sig figs times by 2 sig figs. When I put this 0, it really could have been 0.00, etc., right? 0, 0, 0. It's exactly at 0. So our final answer is going to have 2 sig figs. Now, for car B, so I'm just going to keep checking my time here. Okay, for car B, we have x final is equal to 85 kilometers an hour. Oh, and I'm just recognizing I went from kilometers to meters. I need to keep that the same. So that's kilometers. Okay, and the time frame's the same, 2 hours. We start at school again, so our x initial is just 0 kilometers. And so we're going to take our 85 times by 2. Oops. 85 times by 2. We get 170 kilometers. Okay, so that's how far the two cars were. Okay, both cars pass a gas station 120 kilometers from school. When did each car pass the gas station? So I want you to look at this second part, give that a go, and then when you come back, we'll talk through it.